So for this problem, we have that a student living in a 3 times 4 times 4 meters dormitory room turns on her 100 watts fan before she leaves the room on a summer day, hoping that the room will be cooler when she comes back in the evening. Assuming all the doors and windows are tightly closed and disregarding any heat transfer through the walls and windows, we have to determine the temperature in the room when she comes back 8 hours later. We have to use specific heat values at room temperature and assume the room to be at 100 kilopascals and 20 Celsius degrees in the morning when she leaves. So for this case, we have to consider several things. One is that it is a closed system because it says that the walls are rigid and they are the windows and the door is closed. We have to consider also that it is stationary, so there's no kinetic energy and potential energy. Another thing is that air behaves as an ideal gas. So in the tables we have that. We have to look for the critical pressure of and it's 3.77 megapascals. And it says that we have to disregard any heat transfer, and because it is a dormitory, it has rigid walls, so there's no boundary work and the volume is constant. So now, for the first part, we have to look for the constant R value for air, and in this case we have to look it in the tables A1. So R equals 0.287 kilopascals cubic meter over kilogram Kelvin, and we also have to look for the CV value. So the CV value at 300 Kelvin, it's the room temperature, equals 0.718 kilojoules over kilogram Kelvin. So now, the formula we have to use is that the energy that is going in minus the energy that is going out equals the difference in the energy of the system. And for this specific case, we have that the electrical work that is going in equals the difference in internal energy. And this also can be written as the electrical work that is going in equals the mass times U2 minus U1, that is the difference in internal energy. And this equals also the mass times the CV at room temperature, which we have it here, and it's 300 Kelvin, times T2, the difference in temperature. So now with this, we have the CV, the temperature 1, but we do not have the work that is going in, the mass, and the temperature 2. So now, for the mass, we can calculate the volume of the dormitory because they gave us the size. So the volume equals, it's 3 times 4 times 4, and this equals this equals 48 cubic meters. And we have the volume, we have the pressure, the constant R, and the temperature. So with the ideal gas equation, we can calculate the mass. So we have that M equals the pressure PV over RT. So for this case, we have a pressure of 100 kilopascals, and the volume equals 48 cubic meters, and the R is 0.287 kilopascals cubic meters over kilogram per Kelvin, and and the temperature is 20 degrees Celsius, so it's 293 Kelvin. So this gives us a mass of 57.081 kilograms. So now we have this other value. For the electrical work that is going in, we can calculate, because they gave us the power of the fan. So we have that the power equals the electrical energy that is going in, but it's the flow rate. And this equals 100 watts, which is the power of the fan. And this equals 0.100 kilojoules over second. But we need only the electrical work without the flow rate. So we have to multiply times the difference in temperature to get only kilojoules. So the electrical work that's going in equals 0.100 kilojoules over second. But we have 8 hours. We have to convert it to seconds. So 1 hour has 3,600 seconds. So this gives us 2,880 kilojoules, and that's our electrical work that is going in. So now we have all the data, and we can calculate T2. So I'm gonna erase it. Erase this one. So 2,880 equals 57.08 times the CD, which is 0.718 kilojoules over kilogram Kelvin, times T2 minus 20 degrees Celsius. And if we make that equation to get T2, it's T2 will equal 90.3 degrees Celsius. And that's the result of our problem.